quickly, a little bit about myself. I work for Sapient Global Markets, which is a division of Sapient that focuses mostly on financial applications, like trading applications, risk management, portfolio management, and so on. And I've been passionate about user interfaces for almost 12 years now. I started programming way back when it was Win32 and MFC, jumped on to Java, and then to .NET with WinForms and WPF, and even wrote a book about it called WPF Control Development Unleashed. It's all about custom controls. And off late, I've been doing a lot of work with Mac and the web platform with Grunt, Gulp, Angular, React, and all of those tools for the modern web workflow. My talk today is going to be about UI, not you and I, but UI, user interfaces. Now, if you look at user interfaces in general, right, and this is not going to be a talk about MVC or any of the architectural aspects of user UI development. Instead, I want to give you an engineering perspective, more like a behind-the-scenes look, the internals behind what happens to bring user interfaces to life on the screen. Now, user interfaces have evolved quite a bit from the earliest command line graphics to the bitmap graphic displays for the 90s. This is Next Step. This is Windows 98, 2000, to the modern day desktop interfaces on Yosemite and soon Windows 10. And of course, we can't forget the touch-based animated interfaces of our mobile devices and wearables like Apple Watch and Android Wear. But across the evolution of all of these different interface paradigms, a few things actually have remained the same. It's actually quite surprising. These are the timeless, key concepts, the foundations, which underlie most UI technologies. And the talk today is going to be exactly about that. It's about the fundamentals of UI engineering. Now you may ask, why is this so important, right? I can learn Angular, React, or just pick a native platform and just learn that. But why focus on engineering? It's something different, right? You don't really do it on a day-to-day basis, so why should I know or even learn about it? I'll give you not one, but three good reasons for this. First of all, most of us are going to start with one platform, and then eventually move on to 2 or more different platforms. And even today, a few of them have raised hands about knowing 2 or 3 different platforms, on which they build UIs. So as you move from one platform to the other, you want your skills to be reusable, right? You learn something, some abstraction, some techniques on one platform, and you want that to carry over to all the different platforms you learn and adopt. So that's one reason why you need to understand the basics, the fundamentals. The other is about the fun aspect of learning. Like when you learn a platform like iOS or Android, for example, the way you build UIs in those platforms is very different than the way you do it on the web, perhaps. But even though the terminology-wise, the API-wise are very different, you're still structuring UIs in a very similar fashion. And knowing that helps you to become a little more proficient and even effective as you go from one platform to the other. And lastly, I think most user interfaces actually start out being very simple and soon become very complex. Right? Most projects start out simple, and eventually as you add more features, they become more and more complex. Managing complexity is at the heart of software development. And when you know one platform, and if you solve problems on one platform, it's much easier to kind of borrow them and move them on to the next platform. So it all goes back to fundamentals, right? If you know the fundamentals, it's much easier to actually adopt and learn and become more effective in the next step you take on your career on interface paradigms. Now, the UI landscape in general is a pretty vast topic. So I'm going to break it down into 4 major sections for you. The event loop, the different ways of drawing on the screen, the eventing system, and finally the display pipeline. So let's start with the event loop. A single thread. Most UIs actually run on just one thread. You know that? You guys know that, right? But we run on multi-core processors. We have so many different threads. I can spawn multiple processes, I can spawn hundreds of threads, but yet we run on one single thread, also called as the main thread or the UI thread or the application thread. But why is that? We are in an era of such great advancements in hardware, but yet we are really limited to only one thread. It kind of sounds very surprising or even alarming, actually, right? But it turns out there's actually a very important reason why UIs need to run on a single thread. And this is the science part of it, right, which you never really learn in a classroom or in a university. And nobody really tells you about it. But this is learned through practice and through empirical experiments that you do. You realize that single thread is probably the best way to do it. So let's see why that is the case. So if you look at a typical software stack on any platform, these are probably the high-level architectural layers that you'll have. You start off from the hardware. As you go up, you go to the operating system, the Windows server, and finally on the application layer, right? Now, any UI system has 2 major operations. It's drawing and handling events. That's all there is to it, right? And if you have questions, I think I'm going to take it at the end, just for the interest of time. There's a lot of material I'm covering, so I'm going to take the questions at the end. So hold on to your questions, don't forget them. So drawing and event handling are two important operations that happen in a UI system. Drawing is actually a top-down operation. It starts from the application layer. You issue some APIs, goes to the Windows server, through the operating system, through the drivers, and finally onto your hardware, which is your monitor. Events, on the other hand, travel in the opposite direction. They originate from the input devices like mouse, keyboard, this clicker. These are all events. They're generating the events, and they move up the software stack through your hardware, through the device driver layer, and into the Windows server, and finally onto the application in the form of some event handler with event objects. Now, if you take a step back and look at this picture, and let's say drawing and eventing is done on two separate threads, right? You have two separate threads, and a shared set of resources or layers in between. Now, you probably learned this in Computer Science 101. What happens when you have two or more threads which are using shared set of resources? What kind of problems will you normally have? I heard locking, race conditions, deadlocks, synchronization problems, and in general, messy code, right? This is very complicated to write multi-threaded code. Nobody is an expert at writing it, but over a period of many years, after you lose all your hair, you probably become an expert at it. But we don't want to do that. We want to keep our hair, we want to look smart and nice, right? So if you have these kind of problems, obviously writing UIs will be very complicated. And guess what? The Java AWT team, long time back, actually took this approach. They actually said, let's make separate threads for drawing, a separate thread for events. And guess what? The whole AWT team kind of crashed and burned. Nobody was writing code for them anymore. When they consulted back with the Swing team, they switched back to a single thread. And now, from then on, everyone is using single thread just because of that reason. We don't want multiple threads, and a single thread is the best way to actually write user interfaces. Even though we have all kinds of advancements in technologies today, we're still sticking to this particular paradigm of a single thread. But you'll ask, right? If it's a single thread, there are some inherent properties of a single thread which kind of makes it a little kind of limited. You start out from the first instruction, you go all the way to the last instruction, and then you exit, you quit. Your application quits. But that's not how your user interface is supposed to work. You start off, and then you allow the user to actually interact with the user interface. So you need some kind of a looping mechanism. And that's exactly what an event loop provides. This is the fundamental construct underlying every user interface technology. Event loops, and to go at the heart of it, is a data structure called the event queue. A queue, being a first-in, first-out data structure, takes in operations in the same order and also takes them out in the same order, right? So let's say you have this event loop. It goes around. It's literally a while loop, actually. It goes around and looks at the queue, picks up an operation, and then executes it. And then goes around and does the same thing until all of the operations complete, until it reaches something called an idle state. So as you receive more events, you're going to just put more operations onto the queue, right? This could be network events. This could be input events from your devices. It could even be your own events, which you can put on the event queue. And since this is a queue, they'll be operated and taken out in the same order. So the first one will come out, and then the second, third, the fourth, and so on and so forth. So this happens to be the fundamental concept underlying every user interface technology. Event loops and event queue. Without this, you probably won't be able to function at all. This is like a heart, the beating heart of a user interface. And in fact, you see this concept not just in user interfaces, but also in other single-thread environments. Can you tell me at least one such environment where you have an event loop? It's not UI. Node.js. You guys heard of Node.js? Can you still hear me? OK. So Node.js is a single-threaded environment. And to manage a single-threaded environment, you need a looping mechanism. An event loop provides that. And at the heart of it is an event queue called as KQ when you go to the operating system level. So that's event queues for you. But these event queues have to actually operate in a very efficient manner. Pick out the first operation. You can't be running that operation for too long. Right? Let's say you pick out the first operation and execute it. Now the loop is still waiting for this operation to complete. If you take, let's say, 10 seconds, the UI is going to just hang over there. You have seen the situation, right, where you try to do something and suddenly the UI freezes. You click on it, you scroll, nothing happens. Just like a blank picture, a frozen picture over there. And that's what's happening. The event queue is kind of waiting for that operation to complete, and it's hanging the UI thread. Remember, this is still a thread. It executes operations in a sequential order. So when you take an operation takes too long, it's going to just hang and wait there. But you may ask, right, I'm building a UI, it's a complicated application. I'm going to run long-running processes. How do I do that? So what you do is create separate threads. I mean, this is where threads come in. You use your multiple processors to do this. You create a thread, and this could be a worker thread, it could be a network process, or it could be a server request to say, hey, do this complicated, number crunching, weather forecasting, and come back when you have the results. And when you get the results, you put an operation onto the queue. And you can do this as many times as you want, depending on the complexity of your application. And when all of those operations complete, the results of that need to be shown on the UI. And this is where you put an operation onto the event queue and say, hey, I'm done. Let's show something onto the UI now. And in the same fashion as an event loop works, it'll just take these operations in the same order and then execute them. And eventually you'll see something nice and beautiful on your screen. But the ultimate goal of every user interface is to run at 60 frames per second. I mean, that's the gold standard of a user interface. Why 60 frames per second? Actually, the monitors are the hardware devices on which we display the UI, run at a refresh rate of 60 hertz. So if your UI is in sync with 60 hertz, it's the most buttery smooth experience you can get. It's like beautiful. You scroll and you swipe and you do a bunch of different things and the UI just works, It's beautiful actually. But if it's 60 frames per second per frame, you only get about 16 milliseconds. That's a very tight budget. Right? I mean, 16 milliseconds to do your operation, the little blocks which we had in our event queue, that's a very tight budget. But in reality, in practice, you don't really have all of that 16 milliseconds. There's actually some housekeeping activity that needs to be done. So you're only left with about 10 milliseconds. That's again extremely tight. But for most practical purposes, your event handlers don't run any more than 5 to 6 milliseconds. So you still have a good budget of time. But that's the gold standard you want to meet. 60 frames per second with a 10 millisecond budget. Now, just to illustrate this point a little more, I put a little video together just to show you what happens when you have low frame rate and a very high frame rate like 60 frames per second. You can see the difference, right? It's very stuttery in the beginning. The first two balls are moving not at the right kind of speed or acceleration. It seems like they're stopping in between. It's like something is happening in the background which is kind of making them slow. And that's what happens when you have a frame rate lower than 60 frames per second. In fact, even up to 30 frames per second, you should be fine, but 60 is what you should really be targeting. And at 60, you can see that it's a buttery smooth experience. The ball just moves gradually left to right, your persistence of vision works properly, and everything looks to be proper. So that's all about the event loops. An event loop, single-threaded nature, and the event queue at the heart of it, that's what underlies every user interface technology. So if you forget everything else that I say after this, just remember this. And as you move from one platform to the other, this is what will haunt you or even be your friend if you work with it. Next, we look at drawing modes. The drawing is, of course, a very tangible aspect of user interfaces, right? I mean, without drawing, you wouldn't even know what's really going on the screen. It seems like nothing is working. So drawing is one thing that gives us visual feedback and tells us that, hey, the UI is doing what we expect it to do. Now, it turns out there are only two possible ways in which you can draw something onto the screen: an immediate mode and a retain mode. Let's see what these are. Now, you guys remember the first time you learned graphics programming? I mean, I remember a time when I was working on this BBC microcomputer, and they had this language called Logo, Turtle Graphics. You would say, go to XY location, then draw a line to this XY location, come down, go left, go right, and so on. Something like this, right? You start off by saying, hey, go to this location, go right, go down, come left, go up, and then fill the whole thing with some color. It was nice, actually. It was fun programming this. And I remember spending hours and hours just doing stupid things like this, drawing a circle, drawing a star, or a rectangle. It wasn't fun, not very productive, not very useful to most people. At least to me it was, but for most people it wasn't. It was fun, actually. And that's how you do immediate mode programming. It's a very explicit, a very imperative style of programming. You say that, hey, this is where you need to do what you need to do, and I'll give every specific instruction that you need to follow to render something onto the screen. In contrast, you have retain mode UIs. A retain mode, as the name suggests, is retained. As in, as you go from frame to frame or from refresh rate to refresh rate, you are retaining the object model of the UI. Which means you don't have to render everything from scratch, which is what you need to do on the immediate side. The next frame, nothing remains, because you're not storing in memory what you have from the previous frame. So you got to do the whole thing again from scratch. So in a retain mode, you start out by having this object model of the UI, and then that gives you much nicer abilities and comfort to kind of say, hey, if the little orange box over there changes, just render that orange box. You don't have to render the whole thing. And this you see very common in most of the user interface platforms, and I'll get to that in the next frame, in the next slide. But retain mode is what you need to remember. It's the most popular form of building UIs. And in fact, if you go from, say, iOS to Android or web, this is what you will see again and again and again. But that doesn't mean that immediate mode is a total waste. It's actually quite useful too. So immediate is a stateless kind of drawing, where you don't remember what you draw in the previous step, so you got to redraw everything from scratch. In a retain mode, you have an object model, a in-memory representation of what the UI should look like, and that almost always looks like a tree structure. Your window, then you have views in it, the view has subviews, the subviews have subviews, and so on. So it's like a tree structure, And you can almost visualize it if you look at certain examples like HTML. HTML is an XML structure, which is also a tree structure, and the visual representation in text almost always matches what you see on the screen as well. So it's a nice way of kind of testing your own UI and say, hey, I wanted a button over here, and so you check in your tree where you want the button, and then you see that button coming up on the screen. So it kind of gives you that quick feedback that you're doing the right thing. So DOM, SVG, they're all examples of retain mode UI, and it's again the most popular form of building UIs these days. Immediate mode, Canvas. You guys programmed Canvas anytime before? Our core graphics on Mac. I'm sure there's an equivalent on Android too, or Direct 2D on Windows. These are all immediate APIs, for building up UI. Now, as I said, there are only two ways of doing it: immediate and retain. But then, why do I need to learn these two, right? I mean, retained is the most popular, so let's just stick to retained. Why even care about immediate? Let's just forget about it. But it turns out, when you're building really high-performance UIs, an immediate is your best friend. So let's say you're visualizing this map of a country, which has a lot of little cities in it, and you are showing the population density by the color of the little tile. Now, this can be an explosive amount of path elements if you're building it by SVG. Right? It could be like serious amount of memory consumption just to render all these different elements. Instead, by not doing that, you can pick the immediate mode, where you can just render everything from scratch. You don't have to consume so much memory. Of course, it's a little more CPU intensive, but you can do it on a separate thread and bring all the geo shapes back onto the main thread. So you can do it far more efficiently, and you can have even animations going on in it. So doing it in an SVG way, it will actually consume a lot more memory. So when time comes to build those high-performance interfaces, those high-volume visualizations, which is very common in financial applications, this is the way to go. Immediate mode is your friend. But for all practical purposes, like 99% of the time where you're just caring about the structure of the UI, stick to retained. So that's about the display modes. Now, let's look at eventing, the eventing system. I mean, we're talking about UI over here, right? The user interface. How does the user really interact with the interface? You need events, right? The user has to tell something to the interface and say, hey, I clicked here, do something, I pressed a button. So events is how you do it. And you have different forms of generating those events. It could be all your classic ones, like your mouse and keyboard. And nowadays it's touch, and very soon you'll have voice. You'll have head tracking if you're using a VR kit. Have you guys seen that Oculus Rift by any chance? It looks awesome actually. It has a much higher refresh rate. It's 120 to 90 hertz actually. It's much higher than a monitor. And you need that because of the persistence of vision and the closeness of the UI to your eye. So eye tracking, head tracking, these are all events. And these are all hardware devices which are going to generate the events to you. But most interface paradigms or interface technologies have an operating system and a Windows server to kind of translate those events into something more meaningful. Events are ultimately just interrupts on a hardware. They arrive at your display driver. The display driver kind of generates some information and sends it to the Windows server. The Windows server then wraps it up in a nice event object, and this is what you deal with. And the event object has a lot of different information, like the timestamp and things like the coordinate at which it was clicked. It does also coordinate transformations if it's the different windows. If you have several windows on the screen, the Windows server also picks the one which is the highest in the stacking order, and then makes sure that the event goes to the right window. And before it does that, it also has to do some coordinate transformations. So all of this is being done by these two layers over here, the Windows server and the operating system. Now, there's a reason why I'm emphasizing these two layers. It's actually very important. Most of the time, you don't really deal with it. I mean, it's almost like a black box. You just don't care about it. You just work with the events and your event handlers. And most often, you don't even look at this whole part. But I'll tell you a story where this thing actually became very, very essential. I was working on an app a few years back. It's a WPF app. And the user would click on a specific part of the screen, and it would just crash. I mean, no matter what, we tried several times on our own machines. I would click on the same location. It would not crash at all. But then this user, I don't know what he was drinking in his coffee, he clicked, and the damn thing crashed. So I don't know what is going on. We tried several times, but we just couldn't reproduce it. So eventually, we just sat down next to the user and said, hey, OK, dude, what are you really doing over here? I need to understand this. So he clicked, and boom, it crashed. So what's really going on over here? So it turned out it actually is a display driver problem. And that kind of interfered with the whole thing. We upgraded the drivers, and everything started working. So it makes sense sometimes to know that you need this kind of these layers. And these eventing mechanisms become a little more apparent when you have immediate and retain mode UIs. So in immediate, when the event arrives, you have to do your own manual testing and ensure everything works properly. With retain mode, you have bubbling and capturing, which are the two mechanisms in which the events can propagate up and down the tree, just because you have a tree structure over there. That's all about eventing system. Let's come down finally to the display pipeline, which is like the heart of the whole UI. So far, we've just been building everything in software. To see something finally onto the screen, we need the pipeline, which is where the rubber meets the road, as they say. In short, the display pipeline is essentially doing this. It takes a retain mode UI, generates a flat picture, and sends it to the GPU, and that's what you see on the screen. It has a wide variety of operations it needs to do. In fact, I'll just list a sampling of them over here. But in fact, there's a lot more going on underneath. We can actually compartmentalize all of these into three major buckets: layout, painting, and compositing. And these three actually happen in the same order. First, layout happens, and then you paint in the layout in the rectangle that you identify, and finally composite and generate the picture that you send to the screen. So layout is a step where you identify the rectangle, you paint it, and compositing is where you do all of this different nice blending and opacities and filtering and stuff, and you do it on the GPU generally. There's one thing though, animation cuts through all of them. If you're animating a growing rectangle, you're actually going through all of the subsystems on every frame of the animation. So layout is a top-down process. Recursively goes down, generates the rectangles, identifies the size of the rectangle, and then eventually sends it to the next step, which is painting, which actually happens in an immediate mode. You do your fills and strokes and gradients, and you do it very explicitly. In CSS, you can specify that in a declarative fashion, but this is what the painting process has to do by taking all of those declarative properties and combining them into the single bitmap. And finally, the CPU needs to send something to the GPU, right? This is where the GPU is the one which is responsible to show something onto the screen. So it generates what is called as textures. And in doing so, it follows a very optimized path. Because we have to make sure that we're not generating too many bitmaps. We want to actually ultimately combine everything into one map and send it to the screen. So the GPU, the compositing process actually goes through a series of transformations, kind of simplifying the render tree so that we only have the bare essentials that we can use to generate the next frame on the screen. The ultimate goal, of course, is to be GPU accelerated. This is the day, almost everyone dreams about. We want a GPU accelerated UI so that everything looks fast and smooth. That's all about UI engineering. 4 major topics, and I had to condense it down to like 20 minutes just because of the interest of time here. But this is what is happening. And you move from system to system, from interface paradigms through technologies. These are the things you'll see again and again and again. You may see terminology differences, API differences, but ultimately you're dealing with these 4 subsystems. Now just to show you the difference between CPU-based rendering and GPU-based rendering, I'll have one video to just close off this whole talk. I'll need, I think, 2 more minutes just to run the video. Sorry, let me just make sure.
All right, I introduced to you Leonardo, and he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1. Let me speed it up. Ladies and gentlemen, Leonardo. When we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
In 10,
9, 8,
7, 6, 5, 4, 3, 2, 1.
GPU.
Ladies and gentlemen, science class is now over. Thank you.
So in the same spirit, the science class is now over. You can read a lot more about what I said in these locations. And if you want to continue the conversation, let's do it on Twitter or on the blog. And if you're on the Mac, make sure to check out QuickLens. It's a Mac app to explore user interfaces. Thank you, friends.